All right, it seems to be working. Okay, so thanks for coming. Basically what we want to do today is go over kind of two things, all right? First, the experiment that you're going to do all of this week, which is the sand, the salicylic acid, and the biphenyl. Okay, you're going to separate the three of them. And then the second thing we want to go over, because it'll help you write the hypothesis, is the one you're going to start this week, which is the benzoic acid, the benzocaine, and the biphenyl. So what I want to do is I want to go over the first part in great detail, and then I want to go over the separation scheme, because that's what's going to help you the most, for the second part. So that's basically the goal for today. So what we're looking at is another separation method. So what separation methods have you learned so far? Column chromatography and TLC, which is very similar to column chromatography. How do those two techniques separate things? Based on polarity. Okay, so if you have two molecules that have fairly similar functional groups, but they have differences in polarity, you could separate them. All right. You also learned distillation. How does distillation separate things? Yeah, based on their boiling point, right? So it separates things based on their boiling point. And again, distillation doesn't work for everything. So here what we're going to do is do liquid-liquid extraction. Liquid-liquid extraction, I think you'll use it in almost all the reactions you do in this course, and that includes organic 1 and organic 2. And what it is it's a convenient way to remove acids and bases from organic reactions. And what you're going to find as you study organic chemistry is very many reactions are catalyzed by acids and bases. Okay, lots of reactions require acids and bases to get them to work because they need to either put protons on something or take protons away from something. But at the end of the day, we don't want those acids and bases in our final product. So we need a way to get rid of them. And the primary way that we get rid of them is through extraction. Okay, so that's basically our goal here, and I could take this off the screen because we don't need to see that. All right, so let's take a look. So the first mixture that you're going to do, this is part 1 and part 2 of the experiment, is you're going to take salicylic acid. All right, salicylic acid is a carboxylic acid, and it happens to be also a phenol. Okay, it has an OH bonded to a ring. And you're going to have that mixed with biphenyl. Biphenyl is just two benzene rings hooked together. All right, so this is salicylic acid. This is biphenyl. And you're going to mix it with sand, which is essentially SiO2. It's a network covalent solid, so it's a network of silicons bonded to oxygens, and there's some OHs and stuff in there. Okay, but these are the three molecules that we're going to separate in parts 1 and 2. Okay, so this is our goal, and we're going to separate them based on functional groups. Salicylic acid is commonly found in like acne medications and things like that. Biphenyl is just a relatively inexpensive, completely organic compound, and then obviously sand is sand. So we want to look at how we could separate these molecules. And the first thing that we're going to do is we're going to separate them based on solubility. So two of these molecules are soluble in organic solvent, and one of them is not soluble in pretty much anything. Which of these three molecules isn't soluble in anything with the possible exception of hydrofluoric acid, which it reacts with? Sand, right? You go to the beach, the sand doesn't dissolve in water. The sand also doesn't dissolve in common organic solvents. Okay? So this is not soluble in anything. So what you're going to do is you're going to take 2 grams of a mixture of these three compounds, and you're going to add diethyl ether. So when you take 2 grams of these compounds and you add diethyl ether, 2 of them will dissolve, salicylic acid and biphenyl. One of them will not dissolve, sand. Now, an interesting thing to point out is salicylic acid polar? Kind of, right? Because it has a carboxylic acid group, it has an OH. But it's still soluble in ether. Why? Because it has 7 carbon groups, right? A carbon here and then the 6 in the ring. So it still has enough carbons that it's soluble in ether. So even though it's somewhat polar, and you've learned like dissolves like, relatively speaking, this is a relatively nonpolar molecule. How about biphenyl? Is that soluble in ether? Yeah, right? Because this is nonpolar, right? Only carbons and hydrogens. It's not completely nonpolar because it's got the ring, but it's relatively nonpolar. Only carbon and hydrogen, dissolves in ether. Sand, again, doesn't dissolve in anything. So what we're going to start with is salicylic acid, biphenyl, and sand. We're going to then add ether and then gravity filter. And it's very important that we don't vacuum filter. Why is it super important that we don't vacuum filter? Have you ever heard of an exploding meth lab? Do you know what causes meth labs to explode? Ether. Okay, ether is extremely volatile. The boiling point's like 37 degrees. That's roughly the temperature that you are. Okay, so ether is super volatile, and in the gas phase, it's explosive. If you use vacuum filtration, you're going to cause more of this to go into the gas phase. Namely, you're going to suck it into the basement of the building as a gas, okay, and it could build up theoretically in the basement of the building and cause problems. So please do not vacuum filter this, all right? Volatile ether is explosive. So 2 of these things are going to be dissolving, and 1 is going to stay as a solid. So we're going to have a solid layer, and we're going to have an organic layer. Which one is going to stay on the filter paper as a solid? Sand. And then the other 2 are going to dissolve. Salicylic acid and biphenyl. Now what's really important to note here is people will ask, should I put ether in the organic layer? So should I put ether here? I think it doesn't matter, right? Because organic implies that there's an organic solvent, and the only organic solvent in the system is ether, which we clearly labeled. So you could put ether here, you could not put ether here, and you could get credit either way. It's kind of like when you write a paper, right? There's no one good way to write a paragraph. There's lots of good ways to write a paragraph. There's lots of good ways to write a separation scheme. I'm showing you one of them, but you don't have to have it exactly. Okay, so we've separated successfully our sand, okay, and we should get about 0.666 whatever grams, a third of the 2 grams, as sand. Now, we have salicylic acid and biphenyl dissolved in ether. And we need a way to separate these 2 molecules. Does anybody know what we're going to take advantage of to separate these 2 molecules? Yes, because we're going to add an aqueous solution. So we will take advantage of density because the ether will float on top, just like salad dressing, oil on top of water. Ether's less dense than water, so it'll float on top. But what are we going to take advantage of to actually separate the 2 analytes? In this case, salicylic acid and biphenyl. I think polarity is a good way of putting it. We're going to take advantage of these functional groups. Okay? So in this case, we have a carboxylic acid functional group. And in this case, we don't, right? So we're going to take advantage of the fact that this is a carboxylic acid and this isn't. So the question becomes, if you have a carboxylic acid, what will it react with? Okay? Does anybody know the answer to that question? What do carboxylic acids react with that neutral molecules do not? What's that? Not water, but it's going to be an aqueous solution. Let me ask you a more general question. What do acids in general, are they well known to react with? Bases. Acids react with bases. Carboxylic acids are not an exception to that. Okay, if you have ever seen the reaction of baking soda and vinegar, right? It produces carbon dioxide gas. This is essentially what you're doing. This is a different carboxylic acid, but vinegar contains acetic acid. All right, a 2-carbon carboxylic acid. So in this case, we have this molecule, salicylic acid, and it's dissolved in ether. You could write this as ether, or you could write it as organic. And we add to it sodium bicarbonate, which is essentially baking soda, but it's dissolved in water. So we're not going to add solid sodium bicarbonate. You could do that, but it'll clog your separatory funnel. So we're going to add an aqueous layer of sodium bicarbonate. What do bases do? This is a base. That's what acids do. Okay, acids donate protons, so bases do what? Accept protons. So the question becomes, what specifically about this molecule is the acidic proton? These all have hydrogens, this has a hydrogen, and this has a hydrogen. This OH. Why? Well, there's lots of reasons. The simplest reason is this is a carboxylic acid, and carboxylic acids are acids which donate protons. The less simple reason is you have resonance stabilization between this oxygen and this oxygen, which makes it the most stable when this hydrogen leaves, because that negative charge can be shared through resonance between this one and this one. Okay, but that's the basic idea. So this proton is going to leave, and what you end up with is a carboxylate with a negative charge and the counter ion of Na+. That OH and the ring just goes along for the ride. Does anybody remember? Because this H will go with HCO3 and make H2CO3, carbonic acid. Does anybody remember about the stability of carbonic acid? What happens to carbonic acid at room temperature? H2CO3. It breaks up into water and CO2. Why is this a safety concern? All right, remember, you're doing this. I'm going to have to move the paper. You're doing this in one of these. My art skills aren't so good. What is this thing called? Let me move it up. What is this thing called? A separatory funnel. And you're going to have an aqueous layer, and you're going to have an organic layer. The aqueous layer is, of course, water. The organic layers are ether. They're immiscible. Ether is less dense, so it's going to be on the top. This thing is capped and closed off at the stopcock. What about this reaction is a safety concern if you have a device that is closed and you have this being produced? The gas will build up pressure. So what do you do in order to safely generate carbon dioxide gas? You basically take this entire thing and flip it upside down so that this is sticking up, and you open the stopcock and it'll go shh, and then you close it, and then you just gently move it around, and then you flip it upside down shh, until you stop getting that carbon dioxide venting. And then you can shake it more vigorously, progressively, so that you only have a small amount of CO2. If you have a large amount of CO2, in the best case, the top will come off. In the worst case, and this has happened to people before, the entire glassware will explode. Okay? And that scares people a lot, and potentially you could get cut from that. Okay? So don't do that. Make sure you vent this. So only very gently mix this, get rid of carbon dioxide. As the concentration of the acid decreases, the amount of carbon dioxide you're going to make will also decrease. So when you're barely getting any CO2, then you can shake it more vigorously and regularly vent it. Okay? Here's the million-dollar question. This molecule is, although polar, soluble in ether. What about this molecule? Is this molecule soluble in ether? No. Why not? Right. This is an ionic compound. Okay? Ionic compounds are not soluble in ether, because remember, to dissolve in a liquid, namely water, you have to separate those ions. And to separate the ions, you need a polar solvent. Ether is not polar enough for that. So what is the state of matter of this compound? Remember, it could either be aqueous or organic. If it's not soluble in ether and it is soluble in water, it's aqueous. All right? So, what did we just accomplish here? We took a carboxylic acid, which has a stronger preference to be soluble in ether than in water, and we made it into a sodium salt, which is insoluble in ether and does dissolve in water. So said another way, we removed the carboxylic acid from the ether layer. Remember, our original goal was to separate salicylic acid and biphenyl. So if we can get one of the two molecules into the aqueous layer and leave the other one in the ether, we've accomplished our goal. So what we're going to do here in our separation scheme is we're going to put 5% aqueous NaHCO3. And we're going to end up with an aqueous layer and an organic layer. In our aqueous layer, we're going to have what we could call sodium salicylate. I don't know where my paper went. All right, just so I can spell it properly. Sodium salicylate. And we're going to get carbon dioxide bubbling out, so I'm just going to write it like that. In our organic layer, we still have our biphenyl and our ether. But what happens when you do the liquid-liquid extraction in the separatory funnel? What happens to the ether? Does anybody know? As far as what else gets into it and contaminates it, if you will. Water. The solubility of water in ether is not 0. It's about 1 gram per liter. So when you actively mix these things together, some of the water dissolves in the ether, and there's nothing you could do about that. How we indicate that in our separation scheme is trace water. All right, and that happens anytime you mix an aqueous solvent and an organic solvent. All right, the extent of the trace amount of water is different for different solvents. All right, so we have our sodium salicylate in our aqueous layer. But our goal here is to put 3 solids in 3 different containers, right? We want to put solid this in one container, solid this in one container, and solid this in one container. So right now we have it in our aqueous layer. How do we get solid salicylic acid back? Very good. Add HCl. So we're going to add HCl. So right now, what we have is this molecule dissolved in water. So it's aqueous. We add HCl, which of course is also dissolved in water, so it's aqueous. What do acids do? Donate protons or accept protons? Donate protons. Where does HCl want to donate a proton to this molecule? Right? It wants to go on that O. So what do we get? We get our original salicylic acid back. Notice these are the same. And NaCl, which we all know is soluble in water. Now, remember that when you had this in the separatory funnel, before you added the HCl, you drained the aqueous layer into a beaker. And once it was in the beaker, then you add the HCl. You're actually going to extract several times with about 15 ml portions of sodium bicarbonate. And then you're going to put them all in a single beaker and then add HCl, 6 molar HCl dropwise until this turns basic as tested by pH paper. So when you do that, you're going to have your salicylic acid or your sodium salicylate in the water, and then you add your HCl and it turns back into salicylic acid. What happens to this as far as a state of matter that helps us to isolate this compound? It's a solid. Why is this now a solid? Let's start with the first question. Why isn't it dissolved in ether? This will definitely dissolve in ether. Remember, we dissolved it in ether a little while ago. Why doesn't it dissolve in ether? Remember, we took the aqueous layer and we drained it into another beaker. Where's the ether? The ether is still in the separatory funnel. So the reason that this molecule isn't dissolved in ether is because we drain out the aqueous layer before we add the HCl. So therefore, the ether's not around. Why is it a solid and not still aqueous? Because this molecule is relatively what? Nonpolar. Okay, this molecule is relatively nonpolar. Remember, it has 7 carbons and 3 oxygens. I get how you see it's polar, but relatively speaking, this molecule is nonpolar, so therefore it won't dissolve in water. So what happens? It precipitates out as a solid. Does that make sense? So we drive this molecule into the aqueous layer by turning it into an ionic salt, which is not soluble in ether. We then drain off the aqueous layer so the ether is not present anymore, and we add an acid, and we reform this organic molecule that's not soluble in water, so it precipitates out as a solid. We filter. And now we've isolated this separate from the other two. So what we want to do here is add, I think it's 6 molar, HCl, and then you're going to filter. All right, so our solid is going to be salicylic acid. And our aqueous is simply going to be NaCl. All right, now we have solid sand separated. We have solid salicylic acid separated. So back to our original goal, it's to separate all 3 of these things as a solid. Well, we got this one and we got this one. Now we have to get this one. So right now, we have the biphenyl dissolved in ether with trace water. We need to get rid of the water, and then after we get rid of the water, what do? If you had salt dissolved in water, and you wanted to get rid of the water and keep the salt, what would you do? Evaporate the water. It's the exact same thing here. If you have biphenyl dissolved in ether and you want just the biphenyl, you get rid of the ether by evaporation. Okay? But before you can do that, you have to get rid of the water. Otherwise, you're going to get like a, oily mess, potentially, depending on how much water is there. So let's get rid of the water. We do that, in this case, in 2 steps. First, we add saturated NaCl in water. All right? This is called brine. And when we add this, it basically pre-dries the organic layer. If you've ever had the experience of getting ocean water in your mouth, it's the same idea. The ocean water sucks the water molecules out of your mouth, and you get like a dry feeling in your mouth. It's the same idea here. I think of the Na and the Cl as like little magnets, and they literally attract the water molecules out of the ether layer. But it doesn't work completely well. So we get an aqueous and an organic, and in the aqueous, we get NaCl and water. And in the organic, we get biphenyl, ether, and even less traces of water. I don't know how you can indicate that. I'm just going to write it as trace water again. All right, I'm just going to fold the paper so it'll fit on the screen. So we get even less traces of water. How do we get rid of those even more trace amounts of water? Anhydrous sodium sulfate. Okay, so you're just going to add a spatula tip full of anhydrous sodium sulfate. One mistake that people commonly make is they add way too much of this. If you add way too much of this, what will happen is your ether and your sodium sulfate will all kind of be one mess, and it's very difficult to get your ether off, and you end up losing a bunch of your product. So just a little bit. You don't want a lot. If it free flows, then you're good. What free flowing means is you can see individual chunks of sodium sulfate, as opposed to it clumps up into one big chunk. If it clumps up into one big chunk, then you need to add a little bit more. If it doesn't, free flows, so it's not one big chunk. There may be some chunks, but as long as some of it is free flowing, you're good. All right? So that's basically that. So when you do that, you end up with a solid, which is Na2SO4, and some number of waters. We don't know. It can hold up to 10, but we don't know the stoichiometry here. And in your organic layer, you end up with your biphenyl and your ether. Finally, how do we get rid of the ether? We evaporate. And you guys are going to use the solvent evaporators, but we're going to just evaporate. And our gas is going to be ether. Okay, it's going to be recondensed into a liquid, so it doesn't matter if you put a liquid. And our solid/liquid is going to be biphenyl. And it's important to note that it's a solid/liquid. In the solvent evaporator, you're going to put this in a hot water bath. And the melting point of biphenyl is 69.2 degrees Celsius. So it's very likely you're actually going to melt your biphenyl and it's going to be a liquid. Then when you take it out of the bath, it'll quickly turn into a solid again because the bath is going to be, somewhere around 80 degrees Celsius. So it's really important to realize you may end up with a liquid product. How are you going to know when the ether has completely evaporated or boiled off and you just have liquid biphenyl in your flask? Physically, how will you know that? It'll stop boiling. So a boiling liquid, you see bubbles. It doesn't matter if it's ether or water or whatever. If you see the bubbles and the boiling, then you know that there's still ether there. If you see a liquid but it's not bubbling at all, then it's probably just liquid biphenyl. And it's very common to get liquid biphenyl, okay, because we have to crank up the baths because nobody wants to wait for the ether to evaporate, which is understandable. All right, so to evaporate it as quickly as possible, we crank it up. So that is essentially what you're doing in order to accomplish this reaction. One tip I can give you is label everything. Okay, so if you pour some clear liquid from the separatory funnel into a beaker, just label on there. This was I'm on step 2, and this is the extraction. As best you can label it. Okay, and don't throw anything away, because what can happen is you're supposed to, let's say up here, you're supposed to add a solid and then see a precipitate of salicylic acid. Well, you're supposed to add HCl, and then see a solid salicylic acid. If you add HCl and no solid precipitates, and you've thrown everything else in the waste container, we can't help you fix it. All right, more often than not, it's just that the pH isn't low enough. However, if the pH is low enough and you still don't see a precipitate, we need to find where your compound went. So the more stuff you have for us to look through, the more we can help you. All right, so don't throw anything away. And also try to label everything so you know what's what, because they're all going to be clear liquids. All right, it's easy to tell what's ether and what's water because you can smell the ether. But it's not easy to tell which aqueous layer is which. Okay, so just try to label stuff. All right, so that gives you the separation scheme for the reaction you're actually going to do. Now, in the next 5 or 10 minutes, I want to go over the separation scheme that will help you most for writing your hypothesis for the pre-lab, and also you need this separation scheme anyway for next time. So in the next case, this is part 3 of the experiment. In part 3 of the experiment, we're going to separate 3 different molecules. We're going to again separate out biphenyl. All right, so biphenyl. Same molecule. It's neutral. This time, instead of using salicylic acid, we're going to use benzoic acid. The only difference between salicylic acid and benzoic acid is there's no phenol OH here. All right, so this is benzoic acid. Sodium benzoate is a common preservative in soft drinks and juices and stuff like that. All right? And we're going to use benzocaine. Benzocaine is the stuff in Oragel. All right? So it's basically, it numbs your gums if you have tooth pain or something like this. All right? So this is called benzocaine. So in the previous example, we had sand, an acid, and a neutral molecule. In this case, we don't have any sand or sand-like molecule. So if I add ether, which of these will dissolve? Biphenyl will dissolve. How about benzoic acid? Yeah, just like salicylic acid, benzoic acid will dissolve. How about benzocaine? Yeah, it'll dissolve too. So if I add ether, in this case, all of these molecules dissolve. So there's no way for me to simply get rid of one of them easily by adding ether, and one of them doesn't dissolve, so then I just gravity filter. In this case, they all dissolve, so I can't do that. So you already know how to get rid of salicylic acid, right? What did we do to get rid of salicylic acid? We added a what to draw it into the aqueous layer? A base. So we add a base to draw it into the aqueous layer, and then we separate the aqueous layer out by draining out the separatory funnel, and then we add an acid to reprotonate it and cause it to precipitate. Do you think that'll work for benzoic acid? It will. It works exactly the same way. Okay, that'll work for carboxylic acids that aren't soluble in water. It'll even, to some extent, not that you can isolate them, but you can get rid of them, even for carboxylic acids that are soluble. So this can be gotten rid of the same way. So let's take a look at that. So we start with biphenyl, a neutral molecule, benzoic acid, an acid, and benzocaine, which we'll talk about in a minute, is a base. All right, so what we're going to do is we're going to do ether, then we're going to add 5% NaHCO3, aqueous. The other 95% is water. Okay, so we have first ether, then 5% sodium bicarbonate, which is aqueous. We're going to do this in a separatory funnel. We're going to have two layers, right? The ether layer and the water layer, because the other 95%, as I said, is water. And we're going to separate out one of these molecules. Again, which of these three molecules will react with a base, sodium bicarbonate? Benzoic acid. Specifically, this proton will come off. And what we'll end up with is the aqueous layer containing sodium benzoate, and an organic layer containing biphenyl and benzocaine. Of course, ether, because we added ether. And what happens when you do a liquid-liquid extraction with ether? Using an aqueous layer, what do you get in the ether layer? Water. Traces of water. All right. Now, we have sodium benzoate in the aqueous layer. We drain that off. We get rid of the ether, right? We separate it completely from the ether. What do we add to get it back? 6 molar HCl until it's acidic. I should mention that this also will have CO2 bubbling out, so you again have to be careful. Anytime you're using sodium bicarbonate as an acid, and or as a base, and you make carbonic acid, it will come up to be carbon dioxide and water. So make sure you're careful when you add this, because this is the step you're actually going to do in lab this week. So you are going to get carbon dioxide again. You're going to end up with a solid, which is benzoic acid. And you're going to end up with an aqueous, which is NaCl and water. All right, so benzocaine is now dissolved with biphenyl in ether. So we need to separate these two molecules. Well, it turns out that benzocaine is benzoic acid is an acid. All organic acids can be recognized by the carboxylic acid functional group. That is not to say other protons are not somewhat acidic, but they have the carboxylic acid functional group, so they're particularly acidic. In this case, benzocaine is a base, and this is really important. Bases can be recognized by which functional group? The amine functional group, the NH2. So, if we want to separate biphenyl from benzocaine, if we used a base to separate the acid out, what do you think we might use to separate the base out? An acid. And in our case, sorry, I'm off the screen, we're going to use, I believe, 5% HCl. So let's take a look at what that looks like. If we have benzocaine here, which is dissolved in ether, and we add HCl, which is aqueous. What do acids like to do? Give protons or accept protons? Give protons. So HCl wants to give a proton to benzocaine. There are oxygens and there's nitrogen. Where on benzocaine does it want to take the proton? Said another way, what's the basic part? This lone pair on nitrogen is the most basic part of benzocaine. Okay, so this grabs that proton. We end up with the whole rest of the molecule just goes along for the ride. All right, the ester group just stays, the ring just stays. And over here we have now NH, instead of NH2, we have NH3. What's the charge on this? Plus. That's positively charged, right? Nitrogen wants to have 5 electrons and it only has 1, 2, 3, 4. Remember, count the bonds as 1, count the lone pairs as 1 each, or 2 for a lone pair. So there's a plus charge here. Now there's 2 ways of writing this. You can either write the Cl minus next to it somewhere, or you could write plus Cl minus. Either way. Okay? So this is now an ionic compound. So we changed benzocaine from a covalent compound to an ionic compound. When it changes to an ionic compound, what happens to its solubility? Said another way, what's the state of matter here? In this case, it's actually aqueous because we added aqueous HCl. So we have an ether layer and an aqueous layer. So this molecule dissolves in water. This is called benzocaine hydrochloride. More importantly, what doesn't this molecule dissolve in? Ether. This molecule has no solubility in ether. Why? Because it's an ionic compound. Ionic compounds do not dissolve in nonpolar solvents. So, to get rid of the benzoic acid, we added a base first in order to turn it into an ionic compound. To get rid of benzocaine, we add an acid. And more generally, to get rid of an amine, you can add an acid. All right? I'm not saying it always works, but in this course, this is what we go after. All right? So, we add the 5% HCl. In the aqueous layer, we have benzocaine, HCl. All right, I'm going to write it like that. In the organic layer, we still have biphenyl. We still have ether. And we still have trace water. All right. Now, the benzocaine HCl is in the aqueous layer. How are we going to get it back? How are we going to convert this compound back to benzocaine? Add a base. Why? Because one of these protons is acidic. So if we add NaOH, the OH can grab one of those protons. Okay? And what you end up with is your original benzocaine, now with H2 instead of H3. This part just goes along for the ride. The ring and the ester go along for the ride. And you get water and salt. Okay? What is the state of matter of this? Remembering that you got rid of the ether. You drained off the aqueous layer and you put it in a separate container. This will precipitate as a solid because there's no ether around for it to dissolve in. So this becomes a solid. So what we do, as far as the separation scheme, is we take our benzocaine HCl and we add NaOH. I think you use 6 molar NaOH. Okay, and what you end up with is a solid, which is benzocaine, and an aqueous, which of course has water, and it also has NaCl. All right. At the end of the day, we have biphenyl, ether, and traces of water. Exactly what we had before. We had to go through one extra step to get rid of this benzocaine, but now we're exactly where we started before with the biphenyl. What is the first thing we want to go after here before we evaporate the ether? We got to go get rid of the water. So we add saturated NaCl, okay, and we get an aqueous layer, which is NaCl, and an organic layer, which has your biphenyl, your ether, and even smaller traces of H2O. All right, this is kind of what we call pre-drying. I have to fold my paper again. All right. Now, how do we finish off getting rid of the water? Anhydrous, Na2SO4, and we get a solid, which is Na2SO4 and some number of water molecules. And we get an organic, which is our biphenyl, and our ether. Finally, we want to separate the two of them, and we evaporate. The gas is going to be your ether, which of course we will recondense. And your solid/liquid will be your biphenyl. Remember, biphenyl still has a low boiling point. It's the same molecule. So if it's a liquid, you just wait until boiling stops. You wait till you stop seeing the bubbles. And then you know that that liquid that's left that's not boiling is your product, your biphenyl. All right. In all cases, with the exception of the sand, what are we going to do in order to try to prove that that molecule we isolated is that molecule we think it is? Melting point. So what you're going to want to do is go on Wikipedia or wherever and look up the melting points of all these things before you go to lab. Okay? So you want to have the melting points of all the compounds, and then you want to melt them. One really key thing that I could tell you about melting point is please go slow. All right, don't crank that thing up as high as you can and let it fly through a range of temperatures. Especially when you're near where you think the melting point is, heat it slowly. Because if you heat it slowly, you have a better chance of actually seeing when it melts and the tube actually being that temperature. If you crank it up, what happens is it's really a lower temperature than what it says it is. All right, because it takes time for something physically to heat up. Any questions? All right, this type of material, I'm going to go over it again a little bit next week. This type of material is strongly focused on future quizzes, and this type of material is strongly focused on the final exam. So we don't expect you to get it all at once, but you do need to write these separation schemes yourself and make sure you understand why things are going in different layers. If you understand where everything is going and coming from, you're going to ace all that stuff. All right? So essentially carboxylic acids, how do you get them out of the organic layer? And amines, organic bases, how do you get them out of the organic layer? It'll help you out a lot. All right, any questions? All right, I'm going to turn this off, and that's basically it for today.